Hey, welcome to the Vodcast on section 9.8, which is on mathematical expectation. But before we talk about mathematical expectation, we need to talk about weighted averages, which is something we're going to do in the process of calculating mathematical expectation, and it's something that you actually know how to do already. So what's a weighted average? You do this all the time when you calculate your semester grade, when you're told that the first quarter grade is worth 40%, the second quarter grade is worth 40%, and the final exam is worth 20%. Incidentally, I don't know if you know this, is not how your grade is calculated in pre-calc. We do a running total for first semester that's 80%, and then the final exam is worth 20. Okay, so how should we think about this? Well, let's pretend that we didn't have these weights and the first quarter and the second quarter and the final were all worth the same. Then I would just do a regular average, right? I would do don't have my pen on, 91.5 plus 87.8 plus 82, all divided by 3. So one way I can think about this problem is if I distribute that, divide by 3 to each one of those 3 grades, I have 1/3 times 91.5 plus 1/3 times 87.8 plus, I'm running out of room, 1/3 times 82, right? And if I think about this way, these 1/3 numbers, these are the weights that are applied to each of those 3 grades, right? 1/3 of the total grade comes from 91.5, and 1/3 of the total grade comes from 87.8, and 1/3 of the total grade comes from 82. So if I wanted to change up what weights went with each of those grades, all I would have to do is change those numbers from 1/3 to the weights that I want. So what I would actually do to calculate your grade here would be 0.4 times 91.5 plus 0.4 times 87.8 plus 0.2 times 82. And then do that calculation and figure out what it is. Okay, here's our calculator. 0.4 times 91.5 plus 0.4 times 87.8 plus 0.2 times 82. And I get 88.12. So that is your overall semester grade with these weights. Okay, I'm just going to give you a practice problem to try on your own. Okay, here it is. What would your semester grade be if the teacher accounts for the fact that there were more tests in second quarter than first quarter by weighting the semester grade 32% for first quarter, 48% for second quarter, and 20% for the final? Pause this now. Do this problem. Corinne, I'm looking at you. Pause it now. Everybody pause. Do the problem. I know you didn't do it. Pause it now. Okay. Okay, we're back. So how do you actually do this? All you do is change the weights, and then you get the answer, 91.5 times 0.32 plus 87.8 times 0.48 plus 82 times 0.2, 87.824. So since this person did a little bit worse second quarter than first quarter, and now second quarter is weighted more, changing these weights would bring down your overall average a little bit. Okay, so what does this have to do with what our actual topic for today is, which is mathematical expectation? I think the easiest way to explain what mathematical expectation is in the context of a problem. So let's take a look at this. And actually, let me give you the title here. So when I say mathematical expectation, there are other terms for this exact same process. You're finding the expected value, or you're finding the mean of a probability distribution. All of those terms mean exactly the same thing, and they all apply to what we're going to do right now. So let's look at this problem. Rotter Partners is planning a major investment. The amount of profit X is uncertain, but the financial analysts at the firm give the following distribution of what the outcomes might be. So they might earn the following profits in millions of dollars: 1 million or 1.5 million or 2 million or 4 million or $10 million. And then these profits have different probabilities, right? It's more likely that they're going to earn $2 million than it is that they're going to earn $1.5 million or $4 million, and it's even more unlikely that they earn 1 million or 10 million. So how can we do some sort of prediction about what is the expected amount of money that we could think that this investment returns? And one of the things that is a little bit confusing is that when we say mathematical expectation, we don't necessarily mean what we expect the most likely outcome is going to be, right? The most likely outcome I can tell just by looking at the probabilities here is that I'm going to earn $2 million because 0.4 is bigger than any of the other numbers here on this probability list. The mathematical expectation is more giving me some sort of average. If I were to do the same sort of if I had this same exact situation arise over and over and over and over again, and I made the investment over and over and over and over again, and I got lots of different results. Sometimes I would get $2 million, sometimes I would get $10 million, sometimes I get $1.5 million. I would do this many, many times, and then if I were to average over all those times, what was the output that I got? That is a mathematical expectation. So we have this definition here, right? It does not tell the most likely outcome for the random variable x. Rather, if the random experiment were repeated an infinite number of times, the expected value tells the average value of x over those many repetitions. So how do you do this? Well, you do a weighted average. I'm going to average these particular outcomes with these weights, right? 10% of the time, this is going to happen. 20% of the time, this is going to happen. 40% of the time, this is going to happen. It's almost exactly the same as when we're talking about grades, right? 20% of your grade was from your final, just like 10% of the output that I want here is going to be from this $1 million. Okay, so if I want to do this, I'm going to do this weighted average just like I did with the grades. I'm going to do 1 times 0.1 plus 1.5 times 0.2 plus 2 times 0.4 plus 4 times 0.2 plus 10 times 0.1. So I get 0.1 plus 0.3 plus 0.8 plus 0.8 plus 0.1. So if I add all of these up, I get 1.6 to 2.1. So the expected value for the outcome is $2.1 million. And again, this number is not telling me that most likely what's going to happen is I'm going to earn $2.1 million. In fact, $2.1 million is not here on this list of possible outcomes. I'm guaranteed I'm not going to get $2.1 million. But it's saying in the long run, if I were to make this investment many, many times on average per investment, my return would be $2.1 million. Okay, let's look at another example. Okay, this example problem is about a lottery for a pick three type lottery game. So it explains what it is. You choose a 3-digit number. At the end of the day, a 3-digit number is chosen at random. Oh, at the end of the day twice. Let's cross that out. You can make several bets on a pick three ticket, and this describes one of them, the box bet, in which you win $83.33 if your number has the same digits as the winning number in any order. If you buy a $1 pick three ticket and choose your lucky number 709, what is the expected payoff for this ticket? So this is saying that if I were to pick 709 every day forever, right? One time and buy a $1 lottery ticket. What if I averaged all of my winnings over the million times that I played this, what would be the average amount returned per ticket? Okay. So first off, we don't have any of the probabilities given to us. We have to figure this out. Now, and there's a lot to fill in with this table. What is the profit if I win? Well, you might think 83.33, but in fact, you had to pay $1 for that ticket, and they're not going to return that dollar when you win the 83.33. So your profit here is actually only 82.33, right? When you lose, it's not like you don't win anything. In fact, you lose $1. So it's negative $1 is what you get if you don't win because you lost that dollar that you paid. And now we have to figure out the probabilities that go with each of these. What is the probability that you win? Well, this is a problem that we've done before, right? How many different ways are there to pick the digits 709? Well, again, if you think about like the lottery draw on the television where the 3 balls come up, how many different numbers could come up for the first ball? Well, 7 or 0 or 9, right? So that's 3. And then how many balls are left that could be possible to come up for the second one? Well, if 7 came up, then there's 0 or 9 left for the second one. And then the last one, there's only one option left. So there's 6 different options that could make you a winner. Out of how many different options are possible? Well, how many different 3-digit numbers are there, right? Well, there are 10 options for the first digit and 10 options for the second digit and 10 options for the third digit, right? So this is 0.006, right? So that means the rest of the time I'm going to lose. So that is 0.994. So to calculate the expected value here, again, I use the probabilities as the weights and the profit amounts as the things that I'm weighting. So it's going to be 82.33 times 0.006 plus negative 1 times 0.994. And if I do that calculation, you should do it right now too. So you can see now I pulled up the calculator where I already did this calculation. I got negative 0.50002. What does that mean? That means that on average, if I play the lottery every day forever, I would expect to lose 50 cents per dollar that I spend on the lottery. That 50 cents is gone forever. In other words, that is what the state's profit that's running this lottery game is making per ticket, right? If many people buy lottery tickets, they are keeping an average of 50 cents out of this ticket, even when after they pay off everybody who won. Okay, so those are two examples about expected expected value or mathematical expectation. We will see you next time.